Hey guys, welcome back. We are going to do some more review over symmetry in functions, as well as transformations in functions and inverse of functions. So first, we're going to talk about symmetry with respect to the origin. So when I'm asking, is this symmetric with respect to the origin, I'm also asking, is this an odd function? So if it is symmetric about the origin, then f of the opposite of x will be exactly the same as the opposite of f of x. So f of the opposite of x means change the x's to negative x's. So it's 3 times negative x squared plus 6 times negative x. Okay, so negative x squared. Anytime I have an even power, that will eliminate that negative. So that is the same as 3 times positive x squared. Here's a first power. Okay, so that is an odd power. That does not get rid of the negative. So I've got 6 times negative x, which is negative 6x. The opposite of f of x is the opposite of the entire function, 3x squared plus 6x. So I will distribute this negative and get negative 3x squared minus 6x. These are not the same. So no, this is not an odd function. It does not have symmetry about the origin. Okay, so the same for h of x. So I've got h of the opposite of x, which is 5 times negative x, over 7 times negative x squared. 5 times negative x is negative 5x. And negative x squared is the same as positive x squared, so it's over 7x squared. This fraction has one negative in it. If the opposite of h of x also has one negative, then they will be the same. So the opposite of h of x is negative 5x over 7x squared. So when I have a negative in front of a fraction, I can put that negative on the top, on the bottom, or in front. Either way, it's all the same. These both have one negative, so that means the fractions are negative, so they're both the same. So yes, this does have symmetry with respect to the origin. Okay, here we've got a function x squared times y equals 2x, and we want to know if it is symmetric with respect to the x-axis, y-axis, y equals negative x, or none of those. So to test the x-axis, if it has symmetry about the x-axis, that means it could flip vertically and land right on itself. So for every y, the opposite of y also exists. So the test for the x-axis is opposite of y. So x squared times negative y equals 2x. And if I can algebraically make this match the original, then it will have symmetry about the x-axis. So negative y, and it's to the first power, so that negative does not go away. So this left side is negative x squared y equals 2x. Now this negative isn't in parentheses, so that squared does not make it go away. The right side matches the original, the left side does not. There is no symmetry about the x-axis. So next we test the y-axis. If there's symmetry about the y-axis, then it could flip horizontally and land on itself, which means for every x, the opposite of x also exists. So we will change the x's. Negative x to the second power, even power cancels out that x. So it's the same as x squared times y. This negative does not get canceled out by an even power. This time the left side matches, but the right side does not. So there is no symmetry about the y-axis. Y equals x. If y equals x, then x equals y, and y and x can be substituted for each other anytime I want. So I'm going to change this, change the x's to y's, the y's to x's. So I have y squared x equals 2y. Now I want to solve this. I want to see if I can manipulate it to equal this same thing here. Okay, so in order to do that, let's try to make the left sides match and just see what happens to the right side. So let's divide both sides by y. And that gives me yx equals 2. Okay, so I'm getting closer. Now I need to get x squared on this left side. So I'll multiply both sides by x. And that gives me x squared y, so that matches, equals 2x, and that matches the original. So there is symmetry about y equals x. And then y equals negative x. So if y equals negative x, then x equals negative y. So I can replace every x with a negative y and every y with a negative x. So the x, I'm going to switch it and negate it. It's going to become negative y squared. And the y is going to become negative x equals 2 times, and this x will become negative y. And I want to try to manipulate that so that the left side matches, and then we'll just see if the right side also matches. Okay, so first let's just simplify with all these negatives. This negative has a second power, so it goes away. This negative does not go away, so this left side is negative. This negative does not go away, so the right side is negative. Now I'll divide both sides by negative y, and the negatives cancel, and a y cancels, so I get yx equals 2. And now it actually looks exactly like what we had over here. So I can just multiply both sides by x, and I get x squared times y equals 2x, and that matches the left side and the right side of the original. So there is symmetry about y equals negative x. Okay, now on to some transformations. So we're transforming y, or f of x equals x cubed, and I see two different things that take place here. First, we do inside the function, and it's multiplying, so there is a horizontal dilation by the reciprocal, which is 1/8. And then, outside of the function, there's a positive 5, it goes up 5. Okay, this next one does not have anything inside the function, so the function is right here, x cubed, there's nothing inside of it. We have an absolute value, and we have a 4. The 4 is inside the absolute value, so that goes first. But again, it's not inside the function, so it is vertical. It goes up 4. And then, any negative outputs have to reflect over the y-axis. So negative y's become positive y's. Okay, so what this graph would look like, after I shift up 4, it would look about like that. But all of these negative outputs here, the absolute value says those can't exist, so they go away and they flip up here and become positive outputs. And our last one here, we have two things both inside the function, so they are both horizontal. First we multiply, so there's a horizontal dilation by 1/4. Okay, then we have this -3, so that minus means it goes right, but it doesn't go right 3, it goes right 3/4, right 3/4. Okay, anytime you have a horizontal dilation and translation, you have to do that division. It's basically like we're factoring out this 4. So it's 4 parentheses x minus 3/4 cubed. Okay, so there's our horizontal dilation, and there is our translation. Okay, next up we have absolute value. So we've got a V shape here. We are multiplying outside of the function and then subtracting outside of the function. We multiply first, so there is a vertical dilation by 3. Then minus 7 means it goes down 7. Okay, here we are multiplying inside and then multiplying outside by a negative. So inside first, and that's horizontal. Anything inside is horizontal. Multiplying inside is a horizontal dilation by the reciprocal, so by 1/2. Then multiplying by a negative is a reflection, and since it's outside, it is vertical, so it's flipping vertically over the x-axis. So it will flip over x-axis. And our last one, there is a subtraction inside. Minus inside means it will shift right 3 units. There's nothing here to divide by but a 1. And then adding outside, that will make it go up 5 units. So right 3 and up 5. Identify the parent function, f of x. So we'll do that first. So f of x equals, the parent function here is the square root of x. It is a square root function. And then sketch a graph of g of x based on the transformation. So let's first sketch f of x, and we'll do that dotted. Okay, so square root, we don't do square roots of negative numbers. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, the square root of 9 is 3. Even though that's off the graph, it's a good idea to put that there just so we go to the right spot. Okay, so that is f of x equals the square root of x. Okay, so this transformation right here is a reflection, and it is horizontal because it is inside the function, so we need to flip over the y-axis. Okay, so it's going to flip horizontally. So those will be the new points. And that is what the graph should look like. Okay, then this next one, we've got x plus 3 squared. So f of x equals x squared is the parent function. Okay, so let's graph the parent function. So we have 0 squared, 1 squared, and negative 1 squared are both 1. 2 squared is 4, negative 2 squared is 4. 3 squared is 9. That's a little bit off the graph, but that's okay. Negative 3 squared is also 9. So this is the parent function. Then we have a plus 3 inside the function, which means it goes left 3 units. So we need to take all these points and move them left 3. And this is the new function. Okay, and then we have inverses. An inverse, graphically, is a reflection over y equals x. So when we finish graphing, this should look like a line of symmetry. So to find our new points, all we have to do is find as many good points as we can and take the x and y and switch them. So here I have 3, 5. So I want to turn it into 5, 3. Negative 1, 4 becomes 4, negative 1. Negative 2, negative 1 becomes negative 1, negative 2. And negative 3, negative 6 becomes negative 6, negative 3. Okay, so we have just taken all the x and y coordinates and turned them around. Okay, we want to make sure we actually end at the endpoints and make this as precise as we can. Okay, now notice when it crosses over itself, it's actually right on the line of symmetry. Okay, now when we have a curve, we might have to use some points that aren't exact, but here's a good point here, here's one, here's one. I'll use this also, so I'll just estimate it. Okay, so I've got -1, 2, so I'll graph 2, -1. -3, 1.5, so that's 1.5, -3. -4, 1 becomes 1, -4. And then I have -5, -3, and that becomes -3, -5. Okay, now when I draw in y equals x, that appears to be a line of symmetry, so I know I graphed that pretty well. Okay, now find the inverse algebraically. So f of x, that's the same as y. And to find an inverse, I switch the x and the y. So x equals 3y minus 5. So I'll add that 5. X plus 5 equals 3y. And divide by 3. X plus 5 over 3 equals y. So f inverse of x equals x plus 5 over 3. So this is my inverse. Before I actually claim it as my inverse, though, I'm going to go ahead and check it. So in order to check it, I can do f of the inverse, which means take this inverse and plug it in right here for x. So that's 3 times x plus 5 over 3 minus 5. If I can get this down to equal just x, then I know my inverse is correct. So these cancel, and I get x plus 5 minus 5. And these cancel, and I get x, which means that inverse is correct. Okay, so again, I'll take the x and y and switch them. X equals 3 over y minus 7. Okay, now this is like a proportion. If I just put this over 1, now it is written as a proportion, and a property of proportions tells me I can switch diagonally, so the x and the y minus 7 will switch places. Y minus 7 equals 3 over x. That's a shortcut that cuts out a couple steps for us. Then I can add that 7, y equals 3 over x plus 7. So f inverse of x equals 3 over x plus 7. Now I'm going to go ahead and check it. So I'm taking this 3 over x plus 7 and plugging it in right here for x. So 3 over x plus 7. And then I have minus 7. So x just became 3 over x plus 7. Plus 7 minus 7 cancels. So I've got 3, and I'm going to make that 3 over 1 over 3 over x. Okay, now I can do this outer loop. I multiply those, and that gives me 3x. That's the numerator. Inner loop gives me the denominator, 3 times 1. And the 3's cancel, and I'm down to just x. That tells me my inverse is correct. And a few questions here about symmetry. To what is each symmetric? An even function is symmetric about the y-axis, so it can flip horizontally and land on itself. An odd function is symmetric about the origin, so it has rotational symmetry around the origin. And an inverse of a function, as we just did here, is symmetric about y equals x.